Okay, today we are going to learn to solve exponential and logarithmic equations. Yay, solving exponential and logarithmic. So, now that we can work with the laws of logarithms, we are able to move into solving exponential and logarithmic functions or equations. And to do that, we have to remember that exponential and logarithmic functions are inverse. This is not writing properly again. Inverse functions and have the ability to undo each other. Okay? Now, this ability to undo means that when we have an exponential equation, we can take the logarithm of each side and then set the exponents equal to each other. So here is what this looks like. We have this equation, 3x, 3 to the x power equals 3 to the 6th power. Now, if I take the logarithm of both sides, that means the log of 3 to the x, and set that equal to the log of 3 to the 6th power, right? And I rewrite that as x times the log of 3 equals 6 times the log of 3, right? And then I divide both sides by log of 3. Then I get that x equals 6. Now, that's a lot of steps. So if we remember that when our bases are the same, then what you can do is set the exponents equal to each other, and then solve for the variable. I keep writing weird things on here. Equal to each other and set, and let's see, solve for the variable. So we don't have to do all the steps that we did here if we remember this principle. Now, it's a shortcut, a technique. I generally don't like those, but we will make an exception for this. So we check to make sure that our bases are equal, and then we just set the exponents equal to each other. So x minus 3 will equal 5, and x equals 8. Okay? Here again, our bases are equal, so we can know that 2x equals 4, therefore x equals 2. Again, our bases are equal, so 3x minus 2 equals 4, and 3x equals 6, therefore x must equal 2. And let's scoot this over a little bit for our last one. Here we have, again, bases are equal, so x over 2 equals 4, so therefore x must equal 8. Hope that helps you, because when you look at having to do all of the logarithm steps for numerical bases, or doing it with natural logarithms for bases of e, then it gets a little bit more complicated. Not that you can't do it, but remembering this principle of checking for like bases and then setting the exponents equal to each other takes out all of the extra steps. Okay? Now, we don't always have bases that are equal to each other. So sometimes we have to convert bases on one side or both to ensure that the bases are the same. Okay? Sometimes we have to factor, sometimes we have to convert square roots into fractional exponents. Okay? So we're going to use all the techniques that we've learned so far to do this. Here's our first one. 2 to the x equals 8 squared. Now here our bases are not the same, but 8 is 2 cubed. And we're taking that and squaring it, so what we really have is 2 to the 6th power. So 2 to the x power equals 2 to the 6th, so therefore x must equal 6. Okay? So we just converted our base of 8 to a base of 2 by using prime factorization. Here's another one. Again, our bases here are not equal, so we can't set the exponents equal to each other. But if we know that 81 is really 3 to the 4th power, and then we're taking that to the 5th power, then we know we're dealing with 3 to the 20th power. So 3 to the 2x minus 1 power should equal 3 to the 20th power. Therefore, 2x minus 1 equals 20. 2x equals 21, and x equals 21 halves. Let's look at the next one. Again, we don't have like bases, but 16 is really 2 to the 4th power. We're taking that to the 4x power. Now we have 2 to the 16x power is equal to the 2 to the 32nd power. So we can set 16x equal to 32, divide by 16, and we know that x equals 2. Here we have another one where our bases are not the same. But 125 is what? Let's see, 5 cubed, right? To the 2x minus 4. But 25 is not a base of 5 either, but it is a base of 5 if we look at it as 5 squared cubed, which gives me 5 to the 6th power equals 5 to the 3 times 2x minus 4 power, right? So 6 then equals 3 times 2x minus 4. And if I divide by 3, I get 2 is equal to 2x minus 4. And 2x is then equal to 6, and x is equal to 3. Let's make it a little bit more complicated with some fractional and negative exponents. So 1 over 27 is really 1 over 3 cubed, which is 3 to the negative 3 power. So using our rules of exponents, we can convert fractions into negative exponents, so therefore we're dealing with x equals negative 3. Okay? Here we have something that looks really, really odd. We have 8 and 1/8 and 4, that's just crazy. But 4 is really 2 squared, and that's taken to the 12th power. So that leaves me with 2 to the 24th power. And 1/8 is really 1 over 2 cubed to the 2x power, which is 2 to the negative 3rd power to the 2x power. So that's 2 to the negative 6x power is equal to 2 to the 24th power. So negative 6x equals 24, and x equals negative 4. I know these are kind of crazy, but your brain will eventually wrap itself around and deal with things. Sometimes you can even get it really crazy like this. Here we have like bases, but when we set our exponents equal to each other, so x squared minus 3x equals 4, we see we have a quadratic that we're dealing with. So that's x squared minus 3x minus 4 equals 0. And we can see that we need to factor this in order to solve for x. So we have x minus 4 and x plus 1, so therefore x equals negative 1 and positive 4. And here we have some other craziness. 8 is really 2 cubed, remember, to the negative 2x power. And this is 4 to the 1/4 power. But this is really 2 squared to the 1/4 power, which is 2 to the 1/2 power. And this becomes 2 to the negative 6x power, right? So we can take negative 6x equal to 1/2, divide by negative 6, multiply here by negative 1/6, and we get x equals negative 1/12. So these are kind of crazy, but it uses all the skills that we've been using in the last 2 or 3 units combined to be able to solve these equations. Okay, now let's progress to the reverse of solving exponential functions, and let's solve some logarithmic functions and some logarithmic equations. When we're dealing with logarithmic equations, we can apply the exponential function to both sides, okay, in order to solve. So what we are dealing with here is saying 3 to the log base 3 of x will equal 3 to the log base 3 of 5. Now 3 to the log base 3 of something is going to equal that, so x equals 5. This is based on the principle that it's this principle down here, that anything to the log of that same thing, log base, let's say b, to the log base b of x is just going to equal x. Okay? And the same thing applies for e to the ln of x just equals x. That's another way of putting that in natural logarithm form. So let's try these. Remember, all we're checking for here is that we have the same base. And in our logarithm form, that really looks like the same number that's little. So we can say 2x then equals 3x plus 5. So x equals negative 5. Here again with our next one, check for our same base. If so, we can set the logs equal to each other. So x squared equals 5x minus 6. Bringing everything to one side, we get x squared minus 5x plus 6 equals 0. Now we need to factor. So x and x minus 2 and minus 3. So x equals positive 2 and positive 3. So there are 2 x's for which this holds true. Okay, for this problem here, we really need to use our laws of logs, okay? Because we have things being added together. We have a 2 out in front of here. That 2 means that we have what we're really dealing with is log, oh, this is not writing properly again, log base 4 of x squared. And this plus sign here means that we really have a product going on. So we have log base 4 of negative 4 times x plus 1. Okay? So that's going to be x squared equals negative 4 times x plus 1 now. So x squared equals negative 4x minus 4. And we can subtract everything over, so we get x squared plus 4x plus 4 equals 0. Now we can factor that out, and we get x plus 2 squared equals 0. Setting that equal to 0, we get x equals negative 2. So remember, our logarithm function is the inverse of the exponential function. Okay? Therefore, by that definition, okay, and I've noticed that we have a little bit of a typo here. This should not say b to the x equals 1. It's just log base b of b equals 1. Log base b of b to the x actually equals x. Okay? And then b to the log base b of x equals x. E to the ln of x equals x. Okay? You could also write this one over here as the ln of e equals 1, and the ln of e to the x equals x. So using these formulas and these principles, we can very quickly determine certain almost complicated looking things. So the log base 4 of 4 to the x is just going to equal x. And 3 to the log base 3 of x, by that same principle, is also going to equal x. Okay? So remember, our natural logarithm is just the log base e of something. So the ln of e to the x is x, and e to the ln of x equals x. And that's it for today.